Hi friend, welcome all to my educational channel Math A to Z. In previous class, we already discussed what is order of an element of a group with proper example and explanation. We also discuss some properties or maybe said theorem related to the order of the group. In this class, we also discuss another some property or another some theorem related to the order of the element of group. The first property or first theorem of this class is if order of A equal to n, then for a positive integer m, order of a to the power m is equal to n by GCD of mn. This is the first theorem of the class. Now we go to the proof of this theorem. Proof. First we let order of a to the power m is equal to k. Then from the definition of order, a to the power m equal to the power k is equal to e with the identity. That is a to the power mk equal to e. Also it is given that order of a is n. So we say that n divide mk. Okay, from this relation and from this given relation, n divide mk. Now here we take GCD of mn equal to d. Then there exists integer u v belongs to z such that n equal to du and n equal to dv, where GCD of uv equal to 1, and if this GCD is not equal to 1, then the GCD of mn is not equal to d. So it must be equal to 1. Now we take a to the power m to the power v is equal to a to the power mv, and if we put the value of m, that is this, we get a to the power duv and a to the power e dv, and this is a to the power un, and this can be written as a to the power a to the power n to the power u. So this is e because order of a equal to n, e to the power u equal to e. That is, we get a to the power m to the power v is equal to e. And it is given that, or we first assume that order of a to the power m is equal to k, and we get a to the power m to the power v is equal to e. So we can write here k divide v. Okay, and we get k divide v. This is relation 1. From this relation, if we put the value of m and value of n both sides, we get n equal to dv divide m equal to u du into k, that is v divide uk, and this gives v divide k, because GCD of uv is equal to 1. So v cannot divide u, and we name this relation as 2. Now from 1 and 2 we get k divide v and v divide k, that is v k equal to v, right? That is order of a to the power m is equal to k is equal to v, and we get from this relation v is equal to n by d, and this is written as n by d, that is d is equal to GCD of mn, GCD of mn. This is very important, interesting, and very logical theorem. And the second theorem or second property of the class is, if order of A equal to n, then order of a to the power p is equal to also n, if and only GCD of np is equal to 1. This is second theorem of the class. We know from the first theorem, if order of A equal to n, then order of a to the power p, this is equal to n by GCD of mn. Here m is pn, and it is given that GCD of np equal to 1, that is n by 1 equal to n. So this is the proof of the first part. Here we take this and we get this. Now if we take order of a to the power p is equal to n, and we also write order of a to the power p is n by GCD of pn. Now n by GCD of pn is equal to n, that is GCD of pn is equal to 1. This is the proof of the second part. Now we go to the last property. Last property is, if order of A is infinite, then for any positive integer p, order of a to the power p is also infinite. Here we first take order of A is infinity. Order of A is infinity. And if possible, let order of a to the power p is equal to n. And from the definition of order, we can write a to the power p to the power n is equal to e. And this relation gives a to the power pn is equal to e. And since a to the power pn is equal to e, so we must write order of A less equal to P into N. So order of A less equal to Pn, that is order of A must be finite, and this gives the contradiction of the given hypothesis. So we must have order of A to the power P is also infinite. Okay, this is not n, this is infinity. An application of this property, this is first property, this is very important property. If we take A belongs to G circle and let order of A is equal to 30. Now if we have to find order of A to the power 18, then this is from this formula, this is 30 by GCD of 18, 30. That is 30 by, this is 6, so this is 5. This is 5. Okay, so the order of A to the power 18 is 5. This is very, very important application of important property. Now at the last of this class, we give here 3 important example of group. First example is example 1. Let X be infinite set and P of X be the power set of X. So must be P of X is of infinite order. So order of P of X is infinite. Also we know that P of X, any power set of any set together with the symmetric difference is a group. And in this group, phi is the identity. Phi is the identity element. Now, for any element A belongs to P of X, we have A symmetric difference A. This is equal to A minus A union A minus A, and this is phi union phi. So this is phi, and we say that A square equal to phi for all A belongs to P of X. So every element of this group is of order 2. Okay, that is order of A is 2. That is, for all element of this group is of finite order, but the group is of infinite order. So this is an example of an infinite group whose every element is of finite order, and this type of group is called torsion group. So the torsion group is such that a group with every element of finite order, and this is torsion group, but this is infinite group. Okay, because it has infinite number of elements. Now we take another example. Consider the second example as Z plus. In this group, 0 is the identity element, and only the identity element is of order 1, that is finite, and all the other elements is of infinite order. Okay, so in this group only finite order element is identity element, and all the other element is of infinite order, and in this type of group is called torsion free group. Torsion free group. Okay, so this group is torsion group and this is the torsion free group. And if we take R star dot, here R star is R minus 0. Here the identity element is 1 and the order of identity element is 1 also. Also, order of minus 1 is 2, because we know that minus 1 into minus 1, that is 1, so order of minus 1 is 2. But all the other element is of infinite order. So here we get two elements. Identity is of finite order, and another element minus 1 is of finite order, and all the other element is of infinite order. So we say that R star dot is a group which is neither torsion group nor torsion free group. Okay, so here we know what is torsion group, what is torsion free group. Okay, and this is the today's class. Thank you very much.